In this video, we will look at a different kind of a problem, also known as a transportation problem. Now, a transportation problem is a relatively different problem because the objective you're trying to achieve in a transportation problem is to make sure that we move goods from one place to the other, given the certain number of allowable routes, while making sure that the total cost of transportation stays minimum. So let's look at the example that we will be working with in this series of videos. Just like any other product, we know that there's always a source which supplies a product, and there is a place that is in need of a product, also known as there's a demand for product. If we look at a product like blood units or blood donations, well, the blood donation activities happen all across the countries, and the blood is then taken to the blood banks. But under unforeseen circumstances, there are some places where all of a sudden the demand for blood increases, more than so that the local blood banks cannot supply or meet that demand. So in order to do so, it's critical that the blood units are supplied to the location where it's needed in time, while making sure that the integrity of the product stays intact. Now, this map that you're looking at right now is giving us some information about what routes are available, which cities are we working with, and what is the cost of transportation between these cities. So if you can see right here in this map, we are working with 6 cities. Each city is connected with arrows. In some cases, the arrows are unidirectional, like right here, and in some cases, the arrows are bidirectional. The direction of the arrow means that what is the allowable flow of the product from one city or the other. For example, between Richmond and Louisville, the product can flow between the 2 cities, for example, from Louisville to Richmond, as well as from Richmond to Louisville. However, between Raleigh and Louisville, we can only ship products from Raleigh to Louisville, and it cannot happen otherwise. Now, for each city, you will see either there is a positive number or there is a negative number. A positive number is representing a surplus, that this city had a surplus of 100 blood units. A negative number is depicting the demand, that this city is short by 70 units, so it will be needing 70 units to meet the demand. Finally, each route has a per unit shipment cost associated with it, and we have to keep that in mind. So if you can pay attention, each route has a cost, which is right here, a starting point. In this case, the starting point for Richmond is Louisville, or one of the starting points is. The ending point for this route is Richmond, and allowable amount that needs to be moved between the 2 cities, which is dictated by the demand and the supply right here. The final thing I would like to point out here is that in a transportation problem, it is very easy to determine how many decision variables, or the yellow cells we are looking at, before we set it up. In a transportation problem, the decision variables are always equal to the number of arrowheads that you have in a picture like this. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arrowheads. So 10 arrowheads means we are looking at 10 decision variables. Our objective over here is to minimize the total transportation cost, and our constraints will be derived from the routes, the allowable routes, as well as what is the supply and demand for each city. So let's move on to our Excel sheet and start setting up this problem.